Let's look at how to derive the system of algebraic equations starting from our boundary value problem. So we have our differential equation and we have boundary conditions, which I haven't shown here in the interest of brevity. And we have the shape for the temperature that we have assumed. So the first thing that occurs to me is that, okay, you know what? I can take that shape, that is my piecewise polynomial approximation for temperature, and I can plug it in here, and maybe I'll get my system of algebraic equations in the nodal temperatures. And I tried that, and it turns out it doesn't work. As the kids in my daughter's school would say, eh. Okay. By the way, textbooks don't tell you that, okay? They don't tell you that this approach doesn't work. And in fact, it's quite easy to see that it won't work. So here I have a linear variation. And if I differentiated that twice, I get 0, which means that that's 0. According to this shape, that's 0, but my heat generation is not 0. So it's saying Q equal to 0. That's wrong. It's even worse at the nodes because your slope is discontinuous, which means that the second derivative is not, the first derivative of temperature is discontinuous. Second derivative is not defined. So this approach doesn't work. In fact, you can see that there is no way with this shape I can satisfy my differential equation. In fact, it will satisfy it very poorly with this shape. So what do I do? Here's what people have figured out. Okay, so you know that this approach doesn't work. So what you do is you go from the differential form to a weighted integral form. So this over here is our differential equation. So you take the differential equation, you multiply it by a weighting function, okay? And that weighting function is an arbitrary function. So this is an arbitrary function. And you integrate it from over your domain, so in our case from 0 to L, and that should be 0. The exact solution is going to satisfy that for any arbitrary W, and it's also going to satisfy that. But once I've assumed a shape for the temperature, there's no way I can satisfy this for any arbitrary function. So what do? I say, you know what? I won't satisfy this for any arbitrary W. I'll satisfy it for one particular shape of W. So I'll say, hey, instead of satisfying it for arbitrary function, I'll satisfy it for an arbitrary piecewise polynomial function. That means I assume a shape for W that looks like my like the shape for temperature, and we'll see that in a minute graphically. And then when I have this form of, when I've approximated the weighting function that way, so I have a shape for temperature, I have a shape for W. Now if I plug in that shape into this, out pop my system of algebraic equations in nodal temperatures. And we'll see this, we'll unpack this a little bit more. But there's an important takeaway here. That is, my finite element solution will not satisfy my differential equation exactly. In fact, in this case, it satisfies it poorly. It won't satisfy this weighted integral form for any arbitrary W, but it'll satisfy the weighted integral form for a particular form of W. And and one can show that as I use more nodes, this becomes more and more arbitrary. So it's going to it'll tend to the exact solution, and we'll come back to that. Okay, so which means that to summarize then, we have the weighted integral form, the weak form as it's called, but with a particular shape of W. So our temperature over here is this shape. Our weighted integral, our weight is of this shape, and you can see it's it's the same kind of shape. So we assign values for the weights at the nodes, and then we just do a linear interpolation. And if we plug these two shapes in here, out will pop our algebraic equations, and we'll get the number of algebraic equations that we need to determine the nodal temperatures, and we'll take a look at that. So we'll see we look into some of the details of this process, and it'll give us some very important insights that we can carry into the case studies, the finite element case studies that we'll do in the answer solver.